Okay, dear participant, welcome to the second day of our Malahit School, which deals with artificial intelligence and machine learning. And today I want to introduce Anton Slesarev. He is the head of he is the head of engineering self-driving group in Yandex. He will tell us about modern approaches for developing autonomous cars and how cars drive independently. During his presentation, Anton is going to talk about algorithm of detecting, predicting, localizing, and planning the movement of three-dimensional objects, and how this algorithm help overcome the problems. I remind you, everyone, that you can ask questions in the YouTube chat. And I should inform everyone that we have some problem with, Anton has problem with internet connection today. So I guess that we can start, and I give the floor to Anton. Okay, Anton?
Hello, thank you for introduction. Yes, I'm Anton, and I'm responsible for algorithms and technology in Yandex self-driving car. I'm graduated from Moscow Institute of Physics and Technology and Yandex Data Analysis School. And now I work in this interesting project. But before I start, I would like to inform you that I'm in place with some problem with electricity, and maybe it will be some kind of shutdown, and I will be disconnected. But in this case, I'll try to reconnect in 3 to 5 minutes. In very bad situation, I completely lost connection, and organizers inform you that we change election or something like this. But let's hope that everything will be okay. And first, we'll discuss a driving problem statement, and I'll show you some videos from real rides. After that, we will talk about technology itself. I'll provide overviews of self-driving subsystems, give 1 or 2 examples of algorithms inside each subsystem, and some links on advanced research. And finally, I'll say some words about current state of the self-driving at Yandex. I think nobody will argue that driving is a challenging task. We want to control a car better than average human driver in almost all situations. But it requires to take into account a huge number of aspects, such as lighting condition, road quality, weather, and road situation. Driving rules are similar around the world, so we just need to implement them, right? But it's not completely true. And it's one of our first self-driving rides in Russian innovation town Innopolis. And you can see tractor driving wrong direction on the roundabout. And it's not a unique case. There are so many violations in this town, maybe due to a lack of traffic or lack of police forces, but I've seen too many violations in Innopolis, maybe more than during whole my driving career. People violate rules not only in Innopolis, they violate rules all over the world. It's a video from Tel Aviv, and this is part of one-way road, and you can see a violator, We even need to design violator detection subsystem. And our safety engineer, he really happy that our vehicle execute this situation properly. It's one of my favorite videos. In this case, our vehicle changed lane. It's a lane change without a reason. And only after that, he realized that two bicyclists driving opposite side direction. So it's one of the first cases when AI technology over complete driver. One more example, it's about driving along lanes. Driving, it's not driving along lanes. Lanes could dynamically change due to road work, snow cleaning, and other conditions. So we need to dynamically understand how to drive on free space. Not only vehicles could behave strange. It's a real situation in Annapolis again. It's just a pedestrian jaywalking in the middle of the road with trash bag. And he's not an actor. It's absolutely real. So we need to be ready for such kind of crazy things on the road. This is an example from Las Vegas. Las Vegas, known by light conditions, a lot of advertisement, and it is a party bus with a lot of green lights around it. And it's quite easy to mistakenly detect green traffic light in case this party bus drive right in front of you. So it's an example that even quite simple task of traffic light detection, much harder if you don't want to not make mistakes. And animals, another source of problems. And it's a horse in the center of another innovation city of Skolkovo. It's quite often situation because they have horse training or something like this, and animals will not follow any rules. So we also need to take into account their behavior. I've shown you some video which illustrates that it's a challenging task. And but we are engineers, and engineers could solve any task, right? But how engineers solve complex tasks? Usually we decompose it on subtasks and solve it separately. We can decompose self-driving on 4 main components. It is localization, perception, prediction, and planning. And I'm going to provide you a brief overview of each of these components. And it's a classic way to solve self-driving. Actually, this decomposition occurred 10 years ago in different papers and still very good describes the problem. So localization, say where we situate. So we can use map. Perception, create a model of reality around us. Prediction predicts how this model will develop in future. And finally, choose the best trajectory to drive in this environment. But before we go to software overview, I will say a few words about hardware. Hardware is a really important part of self-driving, and I think it's at least of 50% of self-driving. And it's a typical design of self-driving vehicle. You can see positions of 3 families of sensors: lidars, radars, and cameras. We would like to cover 360 degrees by each family of sensors. So we can aggregate data from each sensor in our main computational unit. In our car, we have a main computational unit situated in the trunk, and it's quite powerful computational unit with modern CPUs, at least 3 GPUs, so we can execute our algorithms and neural networks. Cameras, we have from 6 to 8 cameras, and it's just a common sensor providing video stream to main computational unit, nothing special. We have 4 lidars, central lidar on the roof and 3 lidars on side and in the front of the car. And lidar provides high precision 3-dimensional point cloud. Next family of sensors, radars. Radars, quite common sensor. In almost all modern cars, you can find a radar, and we usually use it for adaptive cruise control. And radars is really a great sensor also. It provides 3-dimensional information with less accuracy than a radar, but at the same time, radar provides velocity of an object. So combination of all sensors gives us an opportunity to create robust perception and prediction algorithms. So let's return to subsystems. Localization. Localization solve the task where we situate, and it uses different sources of information: satellite data, odometry from the vehicle, and lidar localization. I'll give you more details about lidar localization because it's a very specific thing. And the lidar localization from technological point of view solve the task how to match 2 points of 2 sets of points, of 3D points. And we want to find a transform, translation and rotation that minimizes the sum of square error to closest points. And the most known algorithms to solve this task, which is called ICP. So we have two streams of points, some box which is called matcher match points. It could be something very simple. Let's find closest point to each from one set to point from other set. After that, we filter outliers and minimize errors of our transform. Put transform in loop, match points again, you do it iteratively. So as you understand, we need initial approximation for this algorithm. It's quite robust, and there are many modifications of this algorithm. You can use different strategy to match points, to filter outliers. You can use different types of optimizers to find transform, but all algorithms quite similar and difference in speed and robustness. There are other more advanced algorithms. One classic approach, first paper, which is called Lidar SLAM, utilizing normal distribution transform, and difference with previous approach, let's match not points, but some statistics. We can find some surface in some locations, execute distribution in this place, and try to find a place with similar distribution in another set of points. And of course, there are recent approaches using neural networks. For example, in the second paper, which is called Lidar odometer leveraging fully unsupervised convolutional autoencoders, authors use neural networks to execute features, and they match not raw point clouds, but these features to find proper transform. And if we have 3D localization algorithms which can compare two point sets, first we can create a 3D map comparing point sets from different timestamps. It could be really dense 3D map filtered from any noise. And after that, we can compare point cloud, instant point cloud from the car during a ride to this 3D map, and using the same algorithms, localize ourselves. In this video, you can see one of the first 3D maps which we created next to our office. So when we drive in this neighborhood, we can compare point cloud from the vehicle and understand where we're situated. Okay, let's move on. I've told you about Lidar localization, but there are other algorithms in localization. For example, we need to fuse data from Lidar odometry to odometer from the car, to satellite navigation, to accelerometer and gyroscopes data, and companies usually use some filtering. It could be Kalman filtering or extended Kalman filtering. Also, there are a family of vision-only algorithms. The most known, OrbSLAM 2. It's open sourced, and you can use it if you don't want to buy Lidar, but in case you have a Lidar, usually Lidar localization be more robust than vision only. So we talked about localization. Let's move to perception subsystem. Perception, it's about creating model of environment. What objects on environment we need to detect. We need to detect vehicles, pedestrians, some static obstacles. After that, we want to fuse detections and give it to the next subsystem. On this video, you can see the result of LiDAR-only detection by green boxes, visualized vehicles, by yellow pedestrians, and also you can see 2 bicyclists. And it's just one algorithm. Actually, we have at least 4 different ways to detect pedestrians. And let's talk about some of approaches. We don't have description of our LiDAR-only algorithm, but all approaches quite similar. And let's discuss it on by example of the paper, which is called VoxelNet. Actually, I was surprised that this paper published by people from Apple. And I even more surprised that Apple are working on self-driving also. But it's quite a great paper. So if we want to use LiDAR point cloud to detect object, we want to represent point cloud in some digital form. We can split the space by voxels, and in each voxel we can calculate some features, some feature vector. In the simplest case, it could be something like the height of the highest point in the voxel. But in this paper, authors goes further. They train description for each voxel. They use point-wise input and use voxel feature encoders layers. So they train neural network, which provide embedding for each voxel. After that, we can stack embedding of each voxel in 4D tensor. And actually this tensor really similar to image. In case of image, we have white, height, and 3 channels. In this case, we have 3D space, and each space we have feature vector. And so we can use the same neural networks people use for computer vision to detect objects in 4D. So we can use quite common convolutional layers, and as a final layer, we use region proposal network. A region proposal proposes a region where to find cars and pedestrians. So this is a scheme of common approach for 3D object detection. Different approaches varies how to represent 3D point cloud. For example, we can use not bird eye view projection, but frontal view projection. Frontal view projection easier to fuse with image, but bird eye view projection achieve better robustness, needs less data to train. People use different types of architectures, but again, whole idea is the same. What's disadvantage of this approach? To detect object of specific class, we need enough data for this specific class. So in case of rare objects, like, I don't know, small animals or specific pieces on the road, it could be lack of data. To overcome this problem, we create any motion detector. It's our paper on ICRA conference. It's some conference about robotics. And idea quite similar to voxel net detection, but we don't need fully supervised detector here. So we use the same or similar voxel feature encoding layers. So we have the same description as for common architecture. We add temporal context by using not instant 3D point cloud, but we use sequence of point clouds and use it as an input to recurrent neural network. And this network can find moving objects without specific class. And as an output of this network, we have two grids. One grid say if it's an obstacle in this cell, and the second grid execute velocity of an obstacle. So the result of this network, 2D grid, telling us about moving obstacle around our car. So pluses of this network, it finds some unlabeled moving obstacles in 3D point cloud. Disadvantage of this network, due to lack of label. So this network don't tell us, is it a pedestrian or plastic bag or flying next to us or something something else. So this network has a lack of robustness. That's why we use both approaches in our pipeline. We detect known objects such as pedestrians and I don't know, scooters directly. And if we don't know the class of an object, we can use this network and it gives us at least a way to stop. So what else? The prediction is quite developed field of the science, even for self-driving. There are a lot of great data sets. The first and most known data set, which is called Kitty 3D detections, it is a little bit outdated because it's small, but there are some releases of new data sets such as Waymo, Argo, Leaf data sets. They are really good with many classes with large amount of data. So researchers can improve quality of detection network. But what's the problem? Problem that in real life, we work not with detection quality. We need to work with some corner cases. And I'll give you an example of such corner case. It's black cars. What's the problem with black cars? On some lidars, especially on old models, we don't have enough points on on black objects. It's due to low reflectability of a lidar. Of course, we can improve sensors, and modern lidars have more points on black cars, but still, it could be a problem on larger distances. And researchers from Stanford, Anna Petronovskaya and company, proposed an heuristic how to deal with such kind of black cars. If we see a black car in point cloud looks like a hole in point cloud. So let's find holes in point clouds and propose that some objects there. What's the problem with this approach? The problem that puddle on point cloud also looks like a hole in it, because a ray from LiDAR goes to an object, and in case object is a mirror or puddle, it reflects to the sky, and we don't see the return of the point. So some puddles and some black cars could be could have the same shape, and it's impossible to distinguish it. When we asked authors of this paper how to deal with puddles, they said that they don't have puddles in California. Okay, but we have puddles in Russia, and we need to distinguish such kind of objects. We need to develop special neural networks, how to find puddles, some dust, some other objects in the air. And it's a real challenge, and there are no public data set on such kind of objects. So another problem, dirty sensors. In case of rain or dirty weather, source of data become noisy. And we need to clean this data. We need to deal with different types of noise. And there are other imperfections in all types of sensors. Another example, traffic signs have extremely large reflectability, and on some models of lidars, we can see a halo around the traffic sign. So modern perception is not about how to detect cars. It's more how to deal with all these types of noise in sensor data. What else? We also have data from radars. We also can do fusion with camera, and I didn't say a single word about it. We also have static objects. For static objects, we can use other types of algorithms because we can aggregate data through time and to detect very small obstacles, even with not so very dense point clouds. So, as I said, for perception, we have different types of detectors. We combine detectors together, estimates velocity and acceleration of each important object on the scene, and provide these data to the next subsystem to prediction. Why do we need prediction? Because it's not enough to understand current state of the scene. If you want to drive, you need to understand intention of our participants of movement. We want to know if that specific pedestrian are going to run through the road, even if it's not even if it's a violation. maybe he didn't see us. So to solve these types of problems, we use a family of algorithms which is called prediction. Actually, there are different problem statements for prediction task. We can predict trajectories of each vehicle. We can predict occupancy grids, and also we can predict intents. And it's a difference. What's the difference between intent and trajectory prediction? Pedestrian could have intent to cross the road, but he see a fast vehicle, for example, our vehicle, so he need to stop to give away to this vehicle. So intent and trajectory is not the same. And actually we want to have both type of prediction. And here's the visualization of occupancy grid prediction. What's advantages of occupancy grid prediction? For example, we have a crowd of people next to the road, and we want to know if somebody from that crowd would like to jump out in front of the vehicle. So we don't need to know specific trajectory, but we can just, but we want to know if this space cell in front of the vehicle will occupy it in near future. And if it occupied, with which speed pedestrian would move. We also would like to predict trajectories and maneuvers of other participants. It's an example with lane changes. Other car could keep lane, change left, change right, change lanes by different trajectories. And we actually want to know how other vehicles will ride. It's not very developed field. It's quite new field of science. So it's not a perception. Actually, deep learning developed about 10 years ago by perception task, by computer vision, by ImageNet neural network. But prediction is quite new, not so many good data sets. And it's an example of a research paper in this field. It's one of the first good neural network approaches for predicting vehicle trajectories. And I'll try to describe the idea of this paper. As an input, we use images with 3 channels RGB, and by different colors, we encode different types of object. For example, by green, we encode lane labeling. By yellow, authors encode car. And you can see gradient of the yellow, it encodes movement of the car, and so on. So we encode scene by simple image. And after that, we use simple neural network, again, convolutional neural network, which uses as an input common image. And they concatenate image features with state description. State, it's our speed, acceleration, and direction of movement. So we concatenate these image features with state input and use fully convolutional layers to predict probabilities of trajectories. What is trajectories? Authors generate bank of trajectories. They generate them by simulation. it's a part of an article how to generate good bank of trajectories. So they just have 100K to million trajectories, and let's find probability of each trajectory corresponding to the scene. And on the right image, you can see the result of this algorithm. So they have probabilities of trajectories in this bank. It's an interesting approach. As I said, it's one of the first paper. What can we do better? We can enrich scene representation. We can use specific architectures, and we can use not synthetic, but real trajectories collected from real life. And here's description of our approach. My colleagues published a paper on New RIPS conference, which will be in December in this year. And actually approach quite similar to the previous one, but we have a richer representation of the scene. We encode static features by 400 by 400 metrics. We also have time-dependent features like moving of the vehicles, and we encode position of other vehicles in a few seconds frame. We use neural network, but we don't generate trajectory bank synthetically. We collect millions of trajectories from real life. We cluster them on few clusters, and in each cluster, our network find the most probable trajectory and find probability of trajectories in each cluster. So we have, it's important because we have not only one, the most probable trajectory, but we have, it could be a few modes because sometimes you don't know if the car drives to the right or to the left. So it could be multiple choices, and on some stage, prediction don't have enough information to choose the best trajectory. So we have some quantitative results. Our paper called Prank, and we achieved the third place on Argoverse dataset. As I remember, the first place paper from Uber, and the second place some French PhD. I hope he overtrained his network for this dataset. But anyway, it's a quite good result. By metrics, I didn't say how to measure the quality of models. Here people use ADE, it's average displacement. So we just compare output of data set to ground truth and calculate displacement, and FD, it's displacement in the final point of trajectories. So it's comparison on public data. We don't know anything about performance of such networks, and believe it's quite good result. And it's interesting comparison with VectorNet data. So our submission better than VectorNet, and I'll say you a few words about VectorNet right now. VectorNet is an approach from Waymo. Waymo, it's Google self-driving car project, have a subsidiary which is called Waymo, and they have very good results in real life and in publications. So VectorNet, the approach to predict trajectories. And I said that in our approach and in most other approaches, people use representation of the scene in raster format. It's just some matrices with some channels. But it is expensive. We need to choose discretization. We need to choose, we can lose information due to discretization, but low discretization could be very expensive in performance. So vector approaches looks really promising. And it's obvious way to represent, for example, lane map. It's strange to represent map by raster format. But right now, vector networks works not so good in practice. But we believe that vector approaches is the future of prediction networks. As I said, it's a quite new field, but at the same time, there are recently published very good data sets for prediction. Also, it's a new sense. It's a data set by Waymo. So researchers also could participate in development of this field. And it's really great news. And final, but one of the most important subsystem of self-driving, which is called planning, or more general, it is called decision-making. Okay, very brief overview of how decision-making works. We have perception, prediction, and localization as an input. We also have routing, because we know route, it's our goal. We want to go from A to B. And decision-making subsystem need to find the trajectory. More specific, it's need to send commands to the vehicle. It is a steering command, throttle command, and braking command. What's inside is this yellow rectangle. First of all, we would like to analyze situation on the road. We want to do some high-level decision-making. For example, we could decide to change lane. After that, we can choose the best trajectory to execute this lane change. And finally, we would like to convert trajectory to specific commands to the vehicle. And let's look on this decision. So we have a vehicle, we have a scene, we want to build some graph to find free space and best trajectory in this free space and find the ideal trajectory, but not so simple. Let's build some graph. What kind of graph it would be? We need to attribute each vertex, and it's a graph of trajectory. So it have at least two coordinates. We have direction of the vehicle, we have time, velocity, and acceleration. And it is already 6-dimensional graph. And you maybe know that 6-dimensional graph is not very good for optimizing. It's expensive. What should we do? On practice, we usually split trajectory building on different steps. First of all, let's consider each maneuver. In this case, it could be a lane change to the left, to the right, and go straight. for each maneuver, we can calculate geometry, build a trajectory for change lane left, right, and go straight. Geometry planning is about trajectories. After that, we select best trajectory for each maneuver and overall. And for the top of trajectories, we execute speed planner, which provides some speed profile. So on geometry stage, we have only robust approximation of speed. But when we execute lane change, in different situations, we would like to accelerate or to slow down. And speed planner is about choosing the proper speed profile. So this multi-steps approach provides robustness. It have enough performance, but sometimes lack of flexibility. How to measure the quality of decision-making subsystem? We can measure it against human driver, but sometimes it's hard because if we collect data from Moscow taxi drivers, maybe it's not the best ground truth. We can have online measurement like let's calculate some acceleration, not necessary acceleration on real life. We also can measure it in simulator and on large data. And there is no public data sets, at least large data sets for this task. So it's completely commercial and private field right now. And it's not really easy to make public research. So what else? I didn't say about specific graph algorithms. I didn't said about optimization algorithms, and it's extremely complex task how to build constraints for planning, how to choose what optimization problem we should solve. Interesting question, what kind of model of our car should we use, kinematic or dynamic? Kinematic provides better robustness, but in some cases, you want to have dynamic model of the car with sliding tires, deformation, and so on. There are approaches with hidden Markov models for decision making, and we didn't talk about speed at all. No, I've told you about multi-stage planning for performance, but it's really complex topic. We want to be as fast as possible because we need to react on scene change fast. So it is, I've told you about 4 main subsystems of self-driving. It's 4 main subsystems which works inside the vehicle, and we want to improve each of these subsystems and do it better than human, and win human driver in each situation. But that's not all about self-driving. Actually, it's only top of self-driving iceberg. Beneath the water, we have different systems, different computer systems, which gives us approaches to estimate quality, to collect data, to improve our algorithms. And by complexity, it's comparable to algorithms inside the vehicle. I don't have enough time. I'll provide a really brief overview. Simulation. Simulation, we need simulator to estimate quality of our decision-making subsystem. Perception we can measure on static data sets. We can detect some cars, compare it to ground truth, and estimate our precision and recall. For decision-making subsystem, we have feedback loop. Other participants of the road movement, other agents, reacts on our actions. So if we collect data and change our decision-making algorithm, we need to re-simulate agent movement if we want a robust simulation. And but when we have a simulator, if we want to simulate sensor data, it's a challenge. So, for example, we collect data driving on the one lane. Our decision-making subsystem, new version of decision-making subsystem decided to change lane. So we want to put into our pipeline sensor data from other lane. And it's also, we have very sophisticated and interesting results in this application. For example, this paper from Waymo, they try to generate images from other points of view. They collect, they create 3D map, as I described in localization part of my talk. They use similar algorithms, create a 3D map. After that, they can project image textures to 3D map. And when we put camera in another position, if in this 3D map, we can render image with that projected textures. Now, what's the problem with this approach? That resulted image could be quite poor. And for example, it will not have sky because we don't have 3D map of the sky. And to overcome this problem, authors train neural network, generative adversarial network, which use this rendering image as an input and provides photorealistic output. And it works quite well. They provide some really interesting images, and it's really good for simulator. But another approach for such kind of synthetic images, let's collect data and increase the number of data by putting cameras in different positions and generate more data. And it's and here the results. What train? It's a Waymo open data set. So they showed that using such kind of data augmentation can improve detection quality. I usually very carefully think about synthetic data generation because usually it's easier to collect more data and label it, and it's really easy to make a mistake and augment not very good synthetic data. But in this case, it looks really promising and interesting, and I believe that it's possible to use such kind of architectures to increase the size of data sets. Okay, that's all about technologies. What's happening in Yandex? Very brief slides about it, and we will follow to Q&A. Okay, first of all, we collected more than 8 million kilometers in self-driving mode on public roads. And it's quite a large number. It's more than 100 years of human driving, and it is much more data than any human collect during a lifetime. So we believe we still find new interesting cases in our data. So we believe that it's dramatically important to collect more and more real life data to improve and estimate quality of our algorithms. We have a working application in Napolis. You can use Yandex taxi application and order a taxi. And it will be a real self-driving car. By law, we need to have a human inside the vehicle, but he does not sit behind the driving wheel. It sits on passenger seat. And self-driving is not about, it's not only about vehicles. We also working on robot deliveries, and we use very similar technological stack, almost same localization, almost same perception, and so on and so on. So we can apply the same self-driving stack to different applications. We at Yandex focus on self-driving and robot delivery because we have taxi service and Yandex Lavka and Lidar for deliveries, and we have a request for such kind of technologies. But I believe that it could be applicable to much more wider applications. That's all. Thank you for your attention. I'll be happy to answer your questions.
Thank you so much, Anton, for your interesting presentation. And so I think that you solve one of the most difficult tasks. And we have questions, of course. Here, there are a lot of questions in our chat. The first is, one moment. Will the development of autonomous car be correlated with the development of electric cars? Such an interesting question.
It's an interesting question. Actually, electrical cars are very good for self-driving because we want a lot of power for our computational unit. Dynamic of electric vehicles better than common vehicles. So yes, we like EV vehicles, but it's not a blocker for us at all. Current generation of self-driving, we use Hyundai Sonata as a platform. It's completely gasoline.
Okay, and the second question. Anton, are you here?
Yes, I'm here.
Yeah. Is the random sampling a good sampling method to use here? But I don't understand where is here. Why not use cross-validation or stratified sampling, which could consider all the categories?
Is it about perception or prediction? No, I'll try to answer. If we talk about perception sampling, of course, we use all kinds of tricks. For example, if we have not enough data, I don't know, for yellow blinking traffic lights, it's quite a rare event. So we can increase number of samples of yellow traffic light in during our training, and it's really helpful. If we talk about predictions, of course, we use different types of strategies of sampling, because if we sample trajectories, almost all will be straight trajectories when driving inside the lane. So of course, for training, we need different types of sampling strategies.
Okay, thank you. Thank you so much. And the next question is connected with data, and it's my own question. Yeah, you collect a lot of data from sensors, and how you can annotate the huge number of data, yeah? Which tools do you use, and what you should do with voxels? Yeah, you collect images and 3D images, voxels, and how you can describe the task, which patterns you should annotate, for example, for voxels from Lidar.
Okay, no, data labeling system is a really complex system, and we have different tricks to label 3D data. For example, we ask labelers to find object on images. After that, we project rectangles from image to 3D space and ask another people to label 3D position of the object. And it's a iterative process. So we have two-stage labeling to find all objects on the scene. And we developed special interfaces for it.
Mm-hmm. Thank you. And the next question is, if the rays don't reflect from mirror back to the car, can we use sound waves like sonar to detect the object?
We can, for example, Parktronics on vehicles use sound, but that's kind of ultrasonic sensors have a lot of problems. For example, it could false from strong noise. It also don't reflect on some on some types of objects, so it will not cover 100% of problems. So we believe that combination of lidars, radars, and cameras much more robust than ultrasonic, and we don't need additional sensors here.
Thank you. The next question is, to record trajectory, track, and performance of a controller, is it reasonable to calculate the mean square error or normalized mean square error?
Sorry, could you repeat?
Is it reasonable to calculate the MSE or normalized MSE to record trajectory, track, and performance of a controller?
Yes, it's reasonable, and it's exactly how we measure quality of our control and quality of vehicle dynamic. So, but actually it also would be problems from localization quality. So if planned trajectory differs from executed trajectory, it could be a problem in different components. So yes, we track these, and in case of problem, we find the root cause.
Okay, and the next question is connected with Lidar. Is Lidar cost liar? If yes, which can be used to reduce the cost? And I have additional question for you. How I understand that Lidar system is the main system of self-driving car, and but Lidar is not reliable element, I guess, yeah. And there is any replacement for it?
Okay, about the cost, the price for lidars decreased several times for last 3-4 years, and it's still not mass produced. So we believe that LiDARs will be cheaper and cheaper and cheaper. And that's why we also work on our own LiDAR, because it's a really important sensor. If you ask about LiDAR damages, LiDAR hardware problem, as I said, we have 4 LiDARs, 1 central LiDAR and 3 additional. 3 additional is not enough to perform movement, but it's enough to perform emergency stop and parking. So in case of hardware issues, we have a subset of sensors which are more or less enough to safely stop the vehicle. Maybe in future we increase the number of sensors. Some companies put 2 LiDARs from the beginning. We believe it's too much, too expensive, but it's possible.
Thank you. And the next question, will map providers add features to help self-driving cars spot obstacles, or will it be the responsibility of the supercomputers embedded in self-driving cars?
No, first of all, we produce maps by itself. So we don't use third-party providers because we have good algorithms for 3D point clouds, and we can draw map above it. Second, no, we don't use to detect obstacles. We use map to better understand human behavior, to understand traffic rules here, because it's complex. But if we have obstacle in the middle of the road, we detect it in real time. We don't need to put it inside the HD map.
Previously, I asked about the development of autonomous vehicles, but I want to ask that is these technologies will be developed in parallel? Will be developed in parallel?
Sorry, don't get it. Could you repeat?
I get that he wants to ask, will be these technologies which you develop now developed in parallel? I guess that I understand question like this.
No, actually, of course, we are developing many technologies in parallel. It's separate teams work on different parts of self-driving.
And the last question from the chat: what working speed is for self-driving cars for now? What working speed?
No, actually, we follow the rules of the city. We usually have 60 kilometers per hour speed limit. We tested we tested highway autopilot mode on highways, and we tested on more than 100 kilometers per hour speed.
Okay, and I guess the last question from me. You said that you don't rely on artificial data, yeah? But maybe you use reinforcement learning for training virtual car for driving without accident in some virtual reality, and use this model as the initial models for retrain it in real life.
Okay, no, first of all, we almost don't use synthetic data for perception because we believe that we enough real life data. Synthetic data and reinforcement learning could be usable for decision-making subsystem, but I think nobody on the planet don't understand finally how to do it, how to understand and train all corner cases. So right now it's kind of theory. I don't know company which uses reinforcement learning in production and really showed that it is better than ordinary learning.
Okay, thank you. Thank you, Anton. And so we don't have any questions. I guess we can finish today. Thank you so much for your interesting presentation. And
perfect. Thank you. I hope it was useful.
Yeah, we will be glad to see you again. Thank you so much.